We've now defined what the structured perceptron algorithm is, but how well does it work in theory and in practice? We'll first go through a theoretical analysis of the structured perceptron algorithm, and then we'll take a look at how important the search problem is for various tasks. The structured perceptron maintains a list of features that it got wrong. These are used to update the weight vector. We are going to assume that a dataset is linearly separable under features v with margin delta if you can find some unit vector u such that for any wrong answer, the right answer of an example x is going to be at least delta away. So any wrong answer can't be less than delta wrong with respect to these features. And so we'll make use of the fact that u is a unit vector a little bit later. For now, just remember that u is some magic weight vector that does exist that separates the good examples from the bad examples. Thus far, we've been assuming that when we're searching for our output for an answer z, that it's going to be the highest scoring hypothesis. And it actually turns out that we don't have to find the best possible score of a sentence. We just need to find some answer that's a violation. And so that's a technical term. We're going to define a violation as any example z such that this is going to be less than or equal to 0 times your weight vector. And we're just trying to find some output z that scores worse than the truth given an input sequence x. All this means is that even if z isn't the highest scoring answer, that y, what we should be outputting, would not be the answer. Okay, so now let's try to find the number of mistakes we're going to make. So we're going to define our diameter r as the largest violation that we're going to see. So take the difference between the features for y and some output z. What is the largest possible score that you can get? And so that's going to be our diameter. Every time you make an error, your weight vector grows. And so what we're going to prove is that the size of our weight vector can't get too big. And thus, our algorithm can only have a limited number of iterations where it makes mistakes, i.e. it updates the weights. And so we'll actually bound this from two directions. We'll bound it based on the minimum separation between a wrong answer and a right answer, and the maximum separation between a wrong answer and a right answer. And once we have both of these inequalities proved, we'll be able to solve for the number of mistakes that we make. Okay, so let's first prove the lower bound. Let's start off by just writing down our update equation. If we multiply both sides by this weight vector u, but we can notice that the last term is the margin. So we're going to replace the margin with the delta that we defined earlier. And so now that we have that in place, this looks a lot like something we can use induction on. Every time we make an error, we're going to add at least delta to the weight vector. And don't forget about the base case whenever you do induction, but this still works for us because at the 0th iteration, before we begin the structured perceptron algorithm, our weight vector is 0. So every time we do an update, our weight vector is going to get at least delta bigger, and so k times delta. And so this isn't exactly what we want, so we're just going to take the norm of these vectors. And so for any two vectors, if you take the norm of the vectors, the product of that norm is going to be greater than the dot product. You can think about norms as absolute values, and so the absolute values of two numbers are going to be greater if you multiply them than the product of the numbers themselves. Okay, so we can get rid of the unit vector, and we're left with the norm of wk plus 1 is greater than k delta, And so now we're just going to square both sides, and we're done. Okay, great. We've done the lower bound, now let's do the upper bound. Okay, so this is what we want to prove. Let's first start off with the update rule as usual. We're going to take the norm and square both sides. We'll apply the law of cosines, which hopefully you remember from trigonometry. And so once we expand this using the law of cosines, we can see that the definition of the diameter is hidden in there, so let's just replace that. And so now we have something at the end here. We're going to argue that this is always going to be less than or equal to 0. We only update our weights if we make a mistake. And by definition of a violation, that only happens when our hypothesis C scores better than our Y. And so this is always going to be equal to 0 or less than that. So we're going to just replace this last term with 0, and our inequality is still okay. And so we can still do induction. Every time we update our weights, the square of the norm is going to grow by at most r squared. K is the number of times we make mistakes. So now we have proved the upper and lower bounds. And so we can put it together in a sandwich and solve for k. And so k is going to be less than or equal to r squared over delta squared. So what does this mean? Our weight vector only changes when we make an error, but the number of errors that we make is thus limited. And it's limited based on how cleanly our data are separated. That if we can make really large mistakes, that we can get fooled, then that increases the number of errors we're going to make. That is encoded by the diameter. So the diameter basically says how badly we can get fooled by a bad example. At the same time, if we have good separation between a right answer and any possible wrong answer, in the best case, if we had this magical unit vector u, then that will decrease the number of errors that we make. And so this analysis shows that you don't need to find the absolute best answer, but there's a deeper intuition here. What if you can find the answer that gives you the maximum violation? So you want to find the z that is the most wrong, and then update your weights with that. Can that give you better performance? So throughout this course, we're going to see how the theoretical analysis can help us understand algorithms that we're already using and how that might lead to new approaches that might improve our performance. And so that's what happens with finding the maximum violation. So this analysis just relied on finding a violation, but if we can find the most wrong answer, the one that gives us the largest possible violation, can that do better in practice? And the answer is yes. For simple tasks like part-of-speech tagging, it doesn't help much. As you get to more and more complicated problems, though, like machine translation, where the search space is just gigantic, it can help a lot. And so in the bottom right here, we see that finding the maximum violation really does better than competing search techniques in this space. So today we've introduced the perceptron algorithm and its structured extension. However, we're still depending on handcrafted features to solve these problems. As we move forward, we won't be making this assumption, and we'll be using units that look a lot like the perceptron to actually learn features that do a good job at binary classification and also can help us on problems like structured prediction.